Imagine that you're listening to a phone line and buried in the signal there's a 30 kilohertz tone. How do you detect that? Well, to make this concrete, let's say that you have 64 samples N, sampled at 128 kilohertz Fs, and your objective is to detect a 30 kilohertz frequency F. Naively, you might throw this signal into an FFT and measure the magnitude of the 30 kilohertz frequency component. In a 64-point FFT, the index of our frequency will be that frequency multiplied by the number of samples and divided by the sample rate. I'll call this index K. In this case, the frequency magnitude of K is 11. You could then make a decision given this magnitude about whether or not K is a well-represented frequency. Of course, this value depends on both the frequencies and the number of samples, so you'd want to massage it first. But in any case, the FFT is not ideal. I mean, in this example, we're computing 192 complex multiplications and throwing away 98% of the results. A better solution would be a single-point DFT, but it still requires 64 complex multiplications. And there's a smarter solution to this problem. It's called the Goertzel algorithm, and I'll show you how it builds on simple concepts in the frequency domain to reduce the runtime computation. Let's switch over to the Z domain and introduce the complex resonator, the filter that the Goertzel algorithm is based on. You can see in the transfer function that there is a pole on the unit circle when Z is equal to e to the j omega. A pole on the unit circle means infinite gain at that frequency, so the filter resonates strongly with the frequency bin K. Looking closer at the transfer function, we can solve for the Z transform of Y and derive the time domain function. And we arrive to something that looks a lot like the original single-point DFT. In fact, the magnitude of the value in Y of n-1 is equal to the magnitude of the Fourier transform at e to the j omega. The phases are different for reasons that are outside the scope of this video, but just know that you can find the equivalent phase by rotating Y of n-1 by e to the negative j omega times n-1. That being said, this filter is no more efficient than the DFT that we started with. So let's return to the complex resonator's transfer function. We can remove the complex coefficient in the denominator by multiplying the numerator and denominator by the complex conjugate of the denominator. In the z-plane, this looks like adding an aliased pole where z is equal to e to the negative j omega, and then zeroing that pole. After simplifying, the coefficients in the denominator have become real, but notice how a complex coefficient has snuck into the numerator. Well, this actually turns out to be okay, and I'll show you why in a minute. This is the Goertzel filter, of which we'll derive the Goertzel algorithm. And there is an important distinction here between filter and algorithm, relating to how you handle this FIR filter in the numerator. Just like before, we can solve for the z-transform and derive the time domain function. However, this time there are two, one in the numerator and one in the denominator. I'll start with the feedback path in the denominator and define an intermediate sequence W for the output of X. And W in this case refers to the output of the first stage of the Goertzel filter. Let me leave this up here and return back to the feed-forward path in the numerator of the transfer function, this time solving for the output z-transform of Y, given the intermediate sequence W. Now, on its own, if you were to pass each sample through these two stages in series, as the derivation is shown, then you would still be multiplying every sample with the complex coefficient. But notice how Y only depends on the values of W. In other words, this filter has no state. Furthermore, recall how the valuable frequency information is found at the end of the complex resonator sequence. Here's where that distinction comes in. The Goertzel algorithm only computes the values of Y once every n samples. And to be clear, Y sub g is mathematically equivalent to the complex resonator I showed before. We can still equate the magnitude and phase of Y sub g to the Fourier transform of e to the j omega. We can easily compare the cost of the single-bin DFT with respect to the Goertzel algorithm for any n number of samples. Because the Goertzel algorithm assumes real-valued input, we should look to the equivalent single-bin DFT. In this case, the number of multiplications is cut in half. So, up until now, I've described the functionality of the Goertzel algorithm in terms of the FFT because that should be familiar to you, but there are several advantages that the complex resonator gives us. First, we do not need to collect a sample buffer before processing. The filter can operate on samples as they are recorded. Second, n does not need to be an integer power of 2. Third, the resonant frequency can be any value between 0 and the sample rate. It is not restricted to integer values of k. Fourth, if you have m different frequencies to measure, an m number of Goertzel algorithms is more efficient if m is less than log base 2 of n. For example, when n is equal to 64, you can measure up to 5 frequencies before losing efficiency. Here is an implementation of the Goertzel algorithm in Python. I have a function here that accepts a sample buffer, a target frequency, and a sampling rate. For the first phase of the filter, I pre-compute the 2 times cosine omega coefficient up here, and then I process each sample in the input, storing y of n-1 in W1 and y of n-2 in W2. After I've processed all of the samples, then I'll do the second stage of the filter, using W1 and W2 from the last iteration of the first pass. And then I return the magnitude from the function. So if I call this function, passing in the signal from the introduction, as well as the 30 kilohertz target frequency and the 128 kilohertz sampling rate, and I print the magnitude and run it, then you can see it returns 11, which is what we expected. But we can take this one step further actually and plot the FFT of the signal and run the Goertzel algorithm for each frequency bin that the FFT is going to compute. And if we run this code, you can see that the plot of the FFT frequency spectrum is equivalent to the Goertzel frequency spectrum. I'll leave you with one more demonstration. I'll play an audio sample at 44 kilohertz that climbs frequencies between 200 and 1000 hertz. And there will be 4 Goertzel algorithms processing the magnitude of different frequencies every 512 samples. I want you to pay attention to how the dots wobble around the resonant frequencies.